All right, this is for the molecular modeling or computational chemistry lab. This intro is a little bit longer just because you will most likely not have gotten to this in the lecture yet. So we're going to cover this in a bit more detail. So first of all, what can you do with computational chemistry? You can do a lot of things. Certainly you're going to find structures. That's the first thing you have to do pretty much with everything. You have to do geometry optimizations. Figure out the structure of the molecule you're after. You can figure out how that structure varies. Molecules are floppy, you might want to know that. We can get orbital information. We can figure out all sorts of molecular properties, dipole moments, electron affinities, electronegativity, ionization potentials. We can find transition states and barriers, so in reactions. We can get thermodynamic information. We can get spectra, electronic, rotational, vibrational. We can calculate excited states from those, so finding the geometry in excited states. We can get solvent effects, so changing between very different solvents and seeing how that affects some of these properties or reactions. We can get NMR and EPR spectra. We can get molecular interactions, so hydrogen bonding, van der Waals, any sort of dispersion forces. So we can do lots of things. There are unsurprisingly lots of software options for this. So there are many of those. There's an error up here. We are not using Spartan, we're using Gaussian. We used to use Spartan. Gaussian is very powerful. It's a research grade suite. It has a graphical user interface, a GUI called Gauss View. So you will spend most of your time in Gauss View. Gauss View will trigger Gaussian to open, and Gaussian will run and then close. But you can do a lot more in Gaussian than Gauss View will do, and certainly more than you can use Spartan for. Computational costs, though, the calculation time typically goes up as 2 to the n, where n is the number of atoms in your molecule, so small things go quickly, big things go slowly. So a lot of what we'll be doing is focused more on small molecules just because we want to explore a lot of different types of calculations in a short amount of time. In general, though, the name of the game for computational chemistry is finding the level of theory that gives you the accuracy you need in the time you're willing to spend. So there's a trade-off there between accuracy and time. Maximize the theory, minimize the time. All of these involve ultimately wanting to solve the Schrodinger equation. So h hat psi equals E psi, where h hat is the Hamiltonian. That describes the interactions between nuclei and electrons, nuclei and nuclei, and electrons and electrons. So if you had, for example, the molecule H2+, you have 2 nuclei and 1 electron. There we have our distances between those. Our Hamiltonian has this form where we have a kinetic energy term for our single electron. We have potential energy of interactions between the electrons and the nuclei. Technically, we have an interaction between the 2 nuclei, but for the electronic Hamiltonian, we don't have that. If we have H2, we're adding another electron. That's going to add some more terms to our Hamiltonian, decent number. Now we still have a kinetic energy term for each electron. We have potential energy terms for interactions between the electron and nuclei. And then we have this term for interaction between the 2 electrons that depends on the distance between electron 1 and electron 2. That term is called electron correlation because it deals with the interaction of multiple electrons. If we can solve the Schrodinger equation, for example, this is just hydrogen atom, we can get a wave function. So there's our 1s wave function, the 1s orbital. Same thing for atoms. Atomic orbitals can be built up into molecular orbitals. All wave functions, but the wave functions are probabilistic. They're not deterministic. We're not saying the electron is at position x, y, z at time t. We have a probability of finding the electron at that position at a given time. So we'll have to, we want to know energies, we want to know the wave functions. To get the wave functions, we need to solve the Schrodinger equation. There's a problem though, and that's that electron correlation term. And it turns out that that electron correlation term means that you cannot analytically solve the Schrodinger equation for more than 1 electron. It's a tricky problem. It boils down to the fact that electrons, if you want to anthropomorphize them, don't like to get too close to one another. Certainly there's an electrostatic component because they're both negatively charged, but it also has to do with the spin of the electron, so it's a little bit more complicated. In general, they're going to want to spend time on the other side of the atom from one another, or the other side of the nucleus. They're going to try and correlate their motion to avoid it. We can write down the Schrödinger equation, but we can't solve it for more than one electron. So we have to use approximations. So our options are fairly many. We can, first of all, ignore quantum mechanics entirely and say, well, I can't solve it. I don't need to solve it for this problem, so I won't bother with the Schrödinger equation. That is molecular mechanics. We could use variational theory, and we'll talk about all of these theories. Semi-empirical, Hartree-Fock, those are the two big variational theory users, method-wise. We could use perturbation theory, which is used by molar-Plesset perturbation theory, not surprisingly. There are some other approaches. Density functional theory is the biggest one of those. So molecular mechanics or molecular dynamics ignores quantum mechanics entirely. We're going to treat everything like billiard balls connected with springs. We're going to describe those springs basically with what's called a force field. The force field has terms for bonds, angles, torsions, hydrogen bonding, London forces, van der Waals, you name it. The more terms you want, the better the results, but the longer it takes. So for example, bond stretching looks like this. You have some spring constant K, you've got an X squared. So that looks like harmonic oscillator essentially, but just in potential form. Bending has some angles in it. You can improve all sorts of things with this by adding cross terms, like a term that multiplies a stretch force by a bend force and so on. These are generally good for large systems because they're computationally cheap. It's just a lot of Newtonian math. Therefore, they're used for big systems like biology for the large part. You do need to find the force constants, the Ks, the spring constants and whatnot. Usually those are done empirically. So you find some data, you fit that data with a bunch of Ks and go on from there. Examples of that, AM1, not AM1, MMFF, Dryden, Charm, Sybil, UMM, those are all lots of MMs for molecular mechanics. Variational theory is quantum mechanical, and it says basically, well, we can't solve the Schrödinger equation, but we can come up with approximations of it that maybe have not the actual wave function, but have something close to the wave function with a numerical parameter in it. And then I'm going to write down this W integral that has psi star h hat psi in the numerator and then a normalization integral in the denominator. I'm going to calculate W. If psi is the true wave function, I get the true energy. So W is going to give me the energy essentially when I do that. If psi isn't the true wave function, I am guaranteed to get an energy that is higher than the true energy. So all I have to do is calculate W, tweak my parameter, calculate W, tweak my parameter. Eventually I will narrow in on a minimum energy. And I know that that minimum energy is going to be close to the true energy, hopefully, depending on my chosen wave function. But it means I can iterate. So I can narrow in on the true energy. So semi-empirical does this, Hartree-Fock does this. They take slightly different approaches to it. So different wave functions, essentially. Perturbation theory takes a different approach. It splits the Hamiltonian into a part we can solve exactly, and then a part that hopefully is a small contributor, but is going to take care of things like the electron correlation. So you have this h hat plus h prime psi. The advantage to this is now we have a model for the wave function that we can use to try and solve this. So I know what psi is for h hat. I'm hoping that that psi works fairly well for h hat prime. So then I can find E, or I know what E is, because I know h hat psi. I can find E prime, and then I can use that to find maybe a better wave function and iterate. That works better than variational theory for some properties, but one of the problems is it doesn't tell you what the sign of E prime is, so you don't know how close or which side you are of the true energy, which means you can't iterate quite as well. Molar Plesset perturbation theory is the one that uses that. Talk about some of the individual methods. So semi-empirical, we said that's a variational theory. Semi-empirical cheats a little bit. So you start with a set of molecules and a set of experimental data on which you want the method to do well. So molecules with less than 5 atoms, and you maybe want heats of formation for those. You're then going to tweak the calculation, tweak your parameters in the variational theory to get the results that you want on those specific quantities. That's called parameterization. That means it's relatively fast. It's very accurate for systems on which it has been parameterized. It may fail spectacularly for systems on which it has not been parameterized. And smart programs won't let you actually run it on things that it is not going to do well on. So maybe really heavy atoms. AM1, PM3, those are the common ones. So you can see, for example, here's literature for ethane's delta H formation. AM1 does okay on that. It's a small molecule, does pretty well. Thymine doesn't do quite as well for it. Thymine is a little bit bigger, but still decent. Hartree-Fock is a step up from that. It's also a variational method, but it uses a different operator instead of the Hamiltonian. It uses what's called the Fock operator that deals with the electron correlation, not between individual electrons, but between one electron and an average of all the other electrons. That makes it very fast among what are called ab initio from the beginning methods. Relatively accurate, doesn't do some thermodynamics. The results that you get are decent, but depend on the basis set used, which means it makes use of basis sets. So let's talk about basis sets. They are nothing more than a set of atomic orbitals that are used to make the molecular orbitals that you're trying to calculate. So obviously, or hopefully obviously, the bigger the basis set that you use is going to be better, but this is calculation, so bigger is going to be slower. So for example, to make CH4, the minimal basis set would involve the 1s orbitals from the hydrogens, the 1s, the 2s, and the 3 2p orbitals from the carbon. So those are the orbitals that would be involved in the bonding. So we would want to have something representing all of those atomic orbitals. That would be our basis set. We could do better by including some of the higher lying orbitals that are less likely to be populated, hydrogen 2s's, the n equals 3 for the carbons. Ultimately, we would include absolutely every possible atomic orbital, but that's impractical. These are given cryptic names because they're not using straight atomic orbitals, because we still have to worry about electron correlation a little bit, and it turns out that the atomic orbitals are a little bit slower to calculate than some others. So STO 3G, the G stands for Gaussian typically. In general, more characters means a bigger basis set. If you have stars or pluses, those are including tweaks, so polarization in the orbitals or diffuse orbitals. Broad generalizations, the higher the atomic number that you're looking at, the bigger basis set you need, and then the more accurate you want your calculation to be, the larger the basis set you need. Density functional theory is a completely different approach that says all properties of the system can be described by the electron density. It uses functionals, which are relations between functions, just like a function is a relationship between variables. The only problem is the exact electron density functional is still unknown. We don't know what it is. But we can do a lot of approximations that work really quite well. The downside is there's a lot of functionals that have been developed. which means there are a lot of things to try, and there's not really an a priori way to determine which functional will work best for your system. But they are really fast relative to other things and reasonably accurate. So DFT is pretty good. It's fairly common. So here you can see the same functional, or the same basis set with 4 different functionals, and calculating here a vibrational frequency. You can see that they come up with a variety of different vibrational frequencies. You can look at what does best, but you kind of have to look at the literature to see what property or which functional does well for the property that you're interested in. Molar-Plesset we said is a perturbation theory approach. It does well for certain properties, vibrations in general. Some systems, there isn't a lot of rhyme or reason as to which one it will do well on. And remember that perturbation theory doesn't narrow in on what the true energy is the way variational theory does. And it's somewhat computationally expensive. So you can do it, but usually you do 2 or 3 MPs. So calculate E prime, calculate new wave function, calculate E double prime, calculate new wave function. That would be MP2. You can do that 3 times. Generally after that, it's not worth it. There are other methods. So configuration interaction is quantum mechanical. That mixes excited states into the calculation. So putting electron 2 for H2 into the 2s instead of the 1s, you get increased accuracy from that. It's computationally expensive. You can do that with 2 or 3 electrons. CAS-SCF is similar, complete active space, self-consistent field. So that uses a lot more orbitals. It's very good for excited states. CAS-PT2 is kind of the same idea, but uses perturbation theory instead of variational theory like CAS-SCF. So that's even better. We're not talking about those because they're actually fairly complicated to set up. So if we had to sum up this computational chemistry picture, we take the Schrodinger equation, we assume nuclei don't move, that gives us the electronic one. We have a couple of options. We can guess how electrons affect one another, that sort of parameterization. That gives us semi-empirical or density functional. We can do sort of the Hartree-Fock method, which does MOs by using atomic ones that are tweaked a little bit. If we mix in excited states, we can do configuration interaction. Molar-Plesset is kind of like that, so that's one of the possibilities for your perturbation is an excited state. That would get us to the exact. So we have a couple of different options in the direction in which we go for our model, and we're going to explore in this experiment how those calculations are carried out. We're going to look at a variety of things that computation can do, and we're going to compare sort of accuracy and time for a lot of these methods. And we're going to look at it through the lens, ultimately, of astrochemistry, which matches well with what we can do in a reasonable amount of time computationally in vacuum, relatively small molecules. All right. There are helpful getting started videos for Gaussian online. Those are actually YouTube. They're a little bit older. Take a look at those. The Gaussian website is helpful, but it actually is written now for a new version of Gaussian, Gaussian 16, which we do not have. So there's not an exact one-to-one correspondence between what it shows and what you can do, but it's pretty good. If you have questions, of course, feel free to ask.